Extreme Physics.
All right, let's take a look at the 1975 AP exam, question 2. This was similar to the example I gave when we were doing the angular momentum lesson. So we got this a bicycle wheel, and it looks like all the mass is at the edge. You know, we got spokes there, but the spokes are very light compared to the mass of the wheel. So basically, this is a hoop. It's a hoop. I'm going to set up a coordinate system like this, where I'm going to put the origin at the axle. And that's because this dart is going to come in, and it's going to hit, it's going to rotate about this. And we're going to use conservation of angular momentum to figure out how quickly it's rotating. And they gave us... this was R, and let's see if I can draw this straight. That's not too bad. That's not too bad. So we have this dart, and it's coming in, and they said viewed above. This is a top view, it's flying straight. It might be dropping, but it's flying straight along this plane. So there we go. All right, so this has a velocity initial v0, and it has an m0 mass m0, and this had a mass of capital M. All right, we want to know how fast is that thing rotating afterwards. All right, so this is 0, and then afterwards it's going to stick in like that, right? So this would be time 1, and it's going to cause this thing to rotate like that. Now, there is no net torque on the system if our system is just this thing and that, the dart and the wheel. So angular momentum is conserved. So I'm going to make a statement of angular momentum that it is conserved. L initial equals L final. Now, what's a little confusing when you first learn about this is, you know, you think of angular momentum is when something is rotating. Like, for instance, it's easy to understand. You know, okay, this has angular momentum because it's rotating, right? So I got this the wheel spinning, and I can do all kinds of stuff like that. But I wonder why it's doing that. I wonder why it's processing. So I can hold it up like that, and for some reason it starts doing this stuff. Oh, I bet that was loud. I just smacked the microphone with the wheel. But it's not hard to understand that this thing has an angular momentum because it's spinning. What's a little harder to understand is, how does this dart have an angular momentum? Well, it does about this point, because angular momentum, as you will recall, hopefully, is generally, angular momentum is R cross P. And this does have a non-zero R vector at all times, and it also has a momentum, a mass times a velocity. So it has a momentum, and it has R vector. So R cross P is non-zero. They do have right angle components to each other. When we calculate the magnitude, in this case though, we are going to look at just the magnitude of the initial. We're going to look at the moment arm, because the moment arm is going to be the easiest to figure out. The momentum's easy to figure out too. It's just m0 v0 that way. And if we take a look, they actually drew in the question. They drew the line of action. Here's the line of action, and here's R. They give this capital R. That's a value, but this is also R when it comes into contact. This is our little r vector. This is our position vector, right? When they gave you R, they actually just gave you, that was a radius. Capital R was a radius, but this is also the position vector. And it's real easy to find this right here, which is the moment arm, right? This is going to be R perpendicular. So we can just take R perpendicular, the moment arm, and multiply it by R. by the momentum to get the magnitude of the angular momentum. And the angular momentum is going to be, let's see, we got R cross P, and the angular momentum is going to be out of the board. That's the direction. So, all right. Well, that's easy enough to find. It's the same thing as this right here, right? That's the same thing as this right here. These are the same magnitudes, so that is just going to be, R times the sine of theta, right? So that's going to be the magnitude of the initial angular momentum. So we have there, oops. Oh, no, that's a moment arm. And then times M0, V0. All right. So initially, we're just going to use R cross P to find the initial angular momentum. And then afterwards, when it sticks in, we're going to have this thing rotating. So we can actually use I omega 1. Right. So that's going to be the general approach. All right. So, but really, to find the magnitude, we're just going to go R perpendicular times P equals the momentum. The moment of inertia is, let's see, what do we got? Well, we got a hoop, which is going to be mr squared, all the masses at the rim. And then gives moment of inertia, but you can look at that. You go, oh, well, all the masses at the rim, we got those spokes, and they don't have much mass at all. Plus the moment of inertia due to the dart, which is m0, little m0, r squared omega 1. All right. Well, this is just r sine of theta, m0, v0. I'll just solve for omega 1. That's easy enough to do. We got r squared, and we have m plus m0. All right, so there's our omega. That's kind of crowded in there a bit. Let me rewrite that. Omega 1, there we go. All right, well, we can simplify that a little bit. Let's get rid of one of ours. And there we go. That is the omega 1. There, omega 1. Sound 0, yep. All right. So that is our answer to A. That's the answer to A. Omega equals sine theta m0 v0. All right. Next question. In terms of the given quantities, find the ratio, the final kinetic energy of the system to the initial kinetic energy of the system. Let's see. Is mechanical energy conserved in this problem? I don't think so. Whenever we get something that smacks into something and kind of sticks with it, that seems kind of inelastic to me. So let's see. If we get an answer of 1, then mechanical energy is conserved. But let's see what we got here. All right. Well, this seems like kind of a brute force question. I think we're just going to calculate the initial kinetic energy, which is just initial kinetic energy, K0. It's all in translation. It's just 1/2 m0 v0 squared. Well, okay. That wasn't too hard. Let's find the kinetic energy afterwards. Kinetic energy afterwards is going to be all in rotation. 1/2 I omega 1 squared. It's all in rotation. There's not translating, the thing just spinning. The dart hit and everything just starts rotating. So let's take a look at what we got. So K1 equals 1/2 I, which is m r squared plus m0, I guess. R squared. That is the moment of inertia. It's the moment of inertia of a hoop plus the moment of inertia of a glob stuck at the in the edge of the hoop. Omega 1 squared. Oh, okay. So then we got m0 v0 sine of theta divided by r m plus m0 squared. All right, let's put a lot of parentheses there. Right off the bat, I see that we have an r squared here, we have an r squared here, so these can go away. And we have an m over m0. That's going to be squared. We're going to get one of those. Let's do this. Let's say this is 1/2 m plus m0 divided by m plus m0 squared. We're going to square it. M0 squared v0 squared sine of theta, sine squared of theta. All right, we're going to square all that, and right, let's go away. And do we have anything else that can go away? No, I think that's it. All right. So what they want? They want the ratio of what? Final kinetic energy. They wanted K1 to the initial is, all right. K1 is, what do we got? We got 1/2 m0 squared v0 squared sine squared of theta all over m plus m0. All right. Nothing squared there, I guess. And then this is 1/2 m0 v0 squared. All right, 1/2s go away. One of the m's go away. The v0 squared goes away. Oh. All right. And it's a ratio of 2 energies. So we should be unitless. We got kilograms. Yeah, that's unitless. And it doesn't look like it's 1 either, right? It looks like it is less than 1. Yeah, definitely less than 1. All right, there's our answer. The ratio of the initial kinetic, or the final kinetic to the initial, is that. That is question B. All right. Very good. There's 1975.
Extreme Fans.